Hi there. Today we're going to finish up our discussion of concentration by looking at mass and volume fractions. So first, a quick recap. When we talk about the concentration of a solution, we're describing how much solute is dissolved in the solution. And qualitatively, we can say that a solution that has a lot of solute dissolved is concentrated. A solution that has relatively little solute dissolved is said to be dilute. And last time we introduced a way to express the concentration numerically using a concentration scale called molarity. Molarity is a very commonly used numerical measure of concentration. It's defined as the number of moles of solute per liter of solution, and it's essentially the default concentration measure in the fields of chemistry, biochemistry, biology. If you talk to a chemist about the concentration of a solution, he or she will naturally think molarity. But that said, there are other ways to describe the concentration of a solution, and that's what we're going to be talking about today. So one of these is the percent composition, and this describes the relative amounts of substances in a mixture, and that is to say the relative number of moles of substances. And one example that you may have encountered before is the distribution of isotopes in natural samples. So carbon, for instance, naturally contains 98.93% of carbon-12, 1.07% of carbon-13, and trace amounts of other isotopes. And what this means is that if you had a sample of carbon, that 98.93% of those carbon atoms would be of the isotope carbon-12, 1.07% of those atoms would be the isotope carbon-13. This way of describing the composition of a mixture is also called the mole fraction. And you see this a lot with talking about composition of different isotopes of an element. And you'll also see it used a lot with mixtures of gases. So for instance, if you were to look up the composition of the Earth's atmosphere, it will generally be reported in terms of mole fractions. So about 78% of the gas in the atmosphere is nitrogen, about 21% is oxygen, 1% roughly is argon, and then there are very small amounts of other gases. And so these express the fraction of moles, or the fraction of molecules of different types that are in this mixture in the Earth's atmosphere. Now, another type of fractional composition that you'll often encounter is called the mass fraction. And this describes the relative masses of substances in a mixture. And mass fraction it has a simple definition. It's the ratio of the mass of solute to the mass of the solution. And this is frequently encountered in mixtures of solids or liquids. And you'll sometimes see this referred to as percent by mass, or percent weight, or weight per weight percent, or just percent. And so one place where you'll encounter this is geologists will use this to describe, for instance, the composition of the Earth, or the Earth's crust. So the Earth's crust is about 46.6% oxygen by mass, about 27.7% silicon by mass, and so on. So another example where mass fraction is used is in this bottle of hydrogen peroxide. It's labeled 3%, and that 3% is the mass fraction of hydrogen peroxide, and then the other 97% in the bottle would be water. And so you might ask how many grams of hydrogen peroxide are in this bottle of 3% hydrogen peroxide. The volume of the bottle is 946 milliliters. So mass fraction is equal to the mass of the solute, in this case hydrogen peroxide, divided by the mass of the solution. We can rearrange that formula to get the mass of solute is the mass fraction times the mass of solution. In this case, the label tells us that the mass fraction is 3%, so 0.03. The label doesn't tell us the mass of the solution. Instead, it tells us the volume. And if we wanted to figure out the mass of the solution, we would need to know its density. So if we had the density, we could take the number of milliliters of solution and multiply by the number of grams per milliliter. Now, we don't know the density of this 3% hydrogen peroxide solution, but we can estimate it pretty well because in this solution, 97% of it is water. And so this is mostly just a solution of water, and so we can expect that the density of this solution is going to be pretty close to the density of water. And so we can expect that it's going to be about 1.0 grams per milliliter. So using that as our estimate for the density, the mass of our solute hydrogen peroxide is going to be the mass fraction 0.03 times the volume of the solution times the density. So we've got 0.03 times 946 milliliters times 1.0 grams per milliliter. And when we multiply this out, we get that the mass of hydrogen peroxide in this bottle is about 30 grams. So that's a typical calculation that you might be able to do using a mass fraction. Another kind of fractional composition that you'll encounter is the volume fraction. And this is a very similar idea to the mass fraction, except this time you're describing the relative volumes of samples in a mixture. And the definition, volume fraction, is the volume of solute divided by the volume of solution. And this is commonly used in commercial products. It's often used in situations where the way that you make the solution is by mixing together predetermined volumes of different components. And you'll see volume fraction sometimes referred to as percent by volume, or volume per volume percent, or just percentage. So here, for example, is rubbing alcohol solution, isopropyl alcohol. And if you look at the label, it says that the composition is 91% isopropyl alcohol by volume. And so in this case, the label tells you that this is a that this percentage is a volume fraction. Many products will not tell you whether the percent is referring to a mass fraction or a volume fraction. That's kind of annoying. Even worse is that there's a third type of fractional composition which is often used on labels, and this is the mass volume fraction. This is kind of a hybrid measure. It describes the mass per unit volume of a substance in a mixture. And you would calculate this by finding the mass of solute in grams and dividing by the volume of solution in milliliters. And this might seem like a weird thing to do. You're mixing different units, grams and milliliters. It's not quite as crazy as it seems, because especially if you're dealing with a solution involving water, water has a density of 1 gram per milliliter. And so for water, at least, 1 gram is the same as 1 milliliter. And so at least when water is concerned, the number of grams and the number of milliliters is roughly interchangeable. And so this isn't quite as crazy as it looks, although I'll admit it does look pretty crazy. And this is also frequently used in commercial products, and it's sometimes called the weight per volume percent, or again, it's sometimes used just being labeled percent. And one place where you'll see percentages, weight per volume, or mass volume fractions. One product where I've seen this is on vinegar. So this particular vinegar product, looking at the label, it says 5% acidity. And in this case, that 5% means that there's 5 grams of acid per 100 milliliters of vinegar. So when you're looking at products that are labeled with percentages, it's not always clear which type of percentage composition they're talking about. Are they talking about mass fraction? Are they talking about volume fraction? Or is it this mixed mass volume fraction? And I'll be the first to say that that's it's annoying that these products aren't always labeled as to what the percentage represents. But on the other hand, because most of these products involve substances dissolved in water, and water does have this one-to-one relationship between grams and milliliters, generally speaking, the mass fraction and the volume fraction and the mixed mass volume fraction they're pretty similar. And so it's forgivable, I guess, that these are used without always being labeled, but that is something to keep in mind when you're looking at the labels of these products. Is sometimes they will tell you what the percent is that they're using. Oftentimes they won't, but that's just something that we have to live with. And that ends our discussion of concentrations.